is I want to just share something with you. I want you to think about these two compounds. NH3 is ammonia, and CH4 is methane, all right? And so these notes were posted yesterday. You can print them out or you can look at them. And we're going to take a little trip in the Wayback Machine here. We should be able to remember how to draw a Lewis dot structure for these. And I'm going to try to call on you guys here. I'm going to just go off of memory here. Nate Gerke, for the NH3, who's in the center and where do I put the H's? And just remember to unmute your speaker.
Put N in the center and then H's surrounding it.
Okay. And have I forgotten anything on my picture there, Nate? Is that N happy?
No, it's not.
No, what does it need?
Needs another pair of electrons.
Yep, and we could go back and double check, but the electrons are all good here. Grace Jensen for the CH4, thanks Nate, just mute there, and Grace unmute. How would I draw the CH4? And I don't know if Grace, you're still muted there, I think. I'm gonna try it one more time there.
The C is in the middle,
Mm-hmm.
H's go around it.
Yep, okay, thanks. And so if we go really way back, all right, and so everybody can go back to muted. If we go really far back, you know, gosh, we talked about the shape of this thing, 3 bonded atoms, 1 lone pair. This would have been what we called the trigonal pyramidal. And this would have been the tetrahedral shape. And we also did all this stuff, and I'm going to get rid of my pictures of all of you guys. Not that I don't like seeing you, but I want to make sure everyone can see the screen here. So we talked about polar and nonpolar molecules. Now this is really going back, and this was stuff that maybe we didn't feel super comfortable with. So we'd compare the electronegativities between the carbon and the hydrogen. And even if these were different enough electronegativity-wise, let's see here. I think Swasti, is this going to be a symmetrical or a non-symmetrical molecule?
A symmetrical.
And if it's symmetrical, remember we said that we snapped. So even if there were polar bonds, because it's symmetrical, Swasti, what would we say this overall molecule is? Polar or non-polar?
Non-polar.
Perfect. It would be a non-polar molecule. All right, and you're going to see why we're talking about all this stuff in just a second. Let's see here, Chris Short. All right, I've got a trigonal pyramidal. Nitrogen is really electronegative. It's good at attracting electrons. Hydrogen's pretty crummy at attracting electrons. Is this one going to be symmetrical? It's got that sort of 3. It's got 3, but then there's that lone pair. This is really hard to do on the screen. Then there's that lone pair sitting up here. If I approach it from this side, I hit the lone pair. If I approach it from this side, I hit those 3 hydrogens. Is that the same or different there, Chris Short?
Asymmetrical.
It's asymmetrical, so it would be polar or non-polar?
Polar.
There you go. All right, so this is a nice little walk down memory lane, and for some of you, it's a terrifying walk down memory lane because you're like, dude, I never knew polar and non-polar. Well, here's the thing. These molecules, all right, if we were to go in and look at like the molar masses of these guys, molar mass of this one, carbon's 12, hydrogens are 4. So the molar mass of this guy is about 16 grams per mole. And if I looked up the molar mass of this guy, nitrogen's about 14, 15, 16, 17. So these have very similar molar masses. This would be 17 grams per mole. And now I want to share something with you. This guy, CH4, all right? And I got to go back to my little interwebs here to tell you this. CH4 has a boiling point, BP, of negative 258.7 degrees Fahrenheit. That is wicked cold, all right? So at room temperature, all right, at room temperature, this is going to be a gas. Now this guy, NH3, if I go and look at its boiling point, and if you look at it, yeah, they have different shapes, all right? One is nonpolar, one is polar. They have very similar molar masses. This guy boils at a balmy -28 degrees Fahrenheit. Now, that's still pretty darn cold, but that is nowhere near as cold as the boiling point for this guy. So what we're getting at today is we're getting into a discussion of why these things have such crazy different boiling points. And what it comes down to is this idea of intermolecular forces, all right? And we're going to focus on basically 3 flavors of these, all right? We're talking about the forces that exist between neighboring molecules. That's what intermolecular forces are. They are the forces that exist between neighboring molecules. All right, and we're going to break these apart into 3 types. I'm going to pause for just a second. Are folks doing okay here? Anybody need anything? Throw a hand up. Thumbs up there from Lauren. Thank you. We're good. And who on earth is the Who's Heaven? Is that Carter? No, Carter's not there. Who is SB Nation Who's Haven? Hogs Haven. Oh,
That's
well.
cool. That's cool.
Who is it? Cole Taylor?
Yeah.
Get out of here. Cole, it's good to see you. All right, so listen, here we go. The first one, all right, this intermolecular force, which is literally going to be the sort of attraction between one molecule and a neighboring molecule. The first one we want to talk about is called the London dispersion force. Sometimes we refer to it as LDF, all right? They're also known as van der Waals forces. All right, and so those are all kind of just names for them. But what those guys are, if you think about any particular molecule, we talked about CH4 already. CH4 is going to have this structure. And the key is looking at this molecule and recognizing that it is nonpolar. So you think about a nonpolar molecule, all right? Here's another nonpolar molecule, CH4 over here. Now, these hydrogens, right, are going to not have much of an attraction for each other, right? The hydrogens on this guy are very much attracted to the carbon. That's why it's its own kind of little molecule here. And these 4 hydrogens, they like their carbon, all right? But these 2 guys, these molecules, there's really not much of an attraction between them, but there is a slight attraction. And that slight attraction is represented by this little dashed line. And that slight attraction is caused by what we refer to as London dispersion forces or van der Waals forces. And here's how they arise. What you've got to visualize is that on the outside of all of these atoms here, right, are electrons. And those electrons are not in any one space. They might be here, they might be here. They're kind of bouncing around, and we never really know exactly where the electrons are. Now, here's the thing that I want you to consider. Is it possible that at a single moment in time, the electrons kind of gather in one part of the molecule over here, making this side negative? And if that side is negative, then this side of the molecule would have to be positive. And this is only temporary, all right? It is lasting for an instant, all right? A moment later, maybe those electrons are in a different place. But here's what happens, and this is what creates a London dispersion force. This temporary moment of rearrangement of charge creates what we call a temporary dipole. Di means 2, pole means you've got a positive and a negative, a north and a south. So the electrons are kind of gathered over here for just a quick hot second, makes this side of the molecule positive. Now the electrons on this molecule are going to respond because I know that electrons want to be close to a positive charge. So this guy, his electrons would be like, oh, dude, I'm going to be close to you. So a temporary dipole here induces, it creates another dipole over here. So this molecule becomes negative on this side and positive on this side. Opposites attract. And so this interaction here, all right, is caused by the temporary arrangement of electrons. And so this type of intermolecular force, of all three that we're talking about, this one is going to be our weakest of the three. And if I wanted to compare CH4, which is nonpolar, to C2H6, which if I drew it, this would be the C, and then I'd have 1, 2, 3, 4, 5, 6. At the end of each of those bars are H's, all right? This guy and this guy, they kind of look similar, but if I looked at it, this one has a much larger molar mass than this one. So the strength of these LDFs, of these dispersion forces, it increases with increasing mass. So if everything else is the same, if I'm comparing a non-polar molecule here, CH4, to a non-polar molecule, C2H6, if I had to guess, do these guys hold on to their neighbors more or less strongly than these guys? Because these guys have more electrons, you could have a little bit of a larger negative charge, which would make a little bit larger of a positive charge. And so because these charges, because there are just simply more electrons in the larger molecule, this C2H6 would have the stronger intermolecular force. So they hold on to their neighbors more tightly. So this guy would have like the higher boiling point, the higher melting point. This guy's going to have the lower boiling point, the lower melting point. Now, I'm going to pause and I'm going to kick out here and see if you guys have questions so far, because this is really tough stuff to get face to face. And right now, I'm trying to do this literally through the magic of the interwebs. So what questions do you have so far? I hate this. Can I just be honest? Swasti, go.
Okay, so I don't know. So how does this happen? Just so like so there are two elements or molecule and they just like start doing the thing, or does it need certain condition?
All right, it's a great question. I'm going to go ahead and lower your hand. So all of the molecules and atoms, everything has electrons, agreed?
Mm-hmm.
Okay, so think about those electrons at any given moment. They're always on the outside of either the atom or the molecule. And you have to realize they're always moving. Now, it's completely conceivable that at one given instant in time, all of those electrons, which are usually kind of evenly-ish distributed, all those electrons find themselves in one spot. And if all those electrons are in one spot, would that area be pretty negatively charged? If I had all the electrons over here, absolutely. That's the charge that the electrons have. They're negative. So if this part of the molecule is now negative, and it's only temporary because it's there only because the electrons are there for just a moment, then a moment later they're back, right?
Yeah.
But if they're all over here, for this moment, there's a negative charge here, which makes the other side of the molecule positively charged. Then the molecules and atoms around it are going to react to that. Because if I have a bunch of negative charge over here, who's going to be attracted to those negatives? Positives. And so what it does is it creates other charges on the surrounding molecules. It is a temporary phenomenon, and it happens with every single thing that has electrons, which is everything in the universe. This is a tricky concept to get, guys. It truly is, okay? But what I want you to know is that London dispersion forces, van der Waals forces, are the weakest, and they are going to be basically the only thing that is affecting non-polar molecules. All right. All right.
Thank you.
What else? Anyone else want to take a dive into the deep end here? Chris, you look like you are asleep, brother. You are literally in your bed on your pillow.
Yep.
You know what? The advantage to this, you can literally set your alarm clock 30 seconds before class time and you're there in class. It's amazing.
I woke up at 8:58.
I love it. All right. All right, let's check this out here. All right. Next one, I'm going to go back to sharing my screen here. Let's go here. Okay. All right. Come on, come on, come on, come on, come on. I think it's coming. All right. So that was when we were talking about non-polar molecules. There are plenty of molecules that are polar, okay? And so here, NF3, if I think about what NF3 looks like, NF, I'm not going to draw all the valence electrons around the F. I'm going to put it on N. This one definitely is going to be, it's got a pull on those electrons towards the fluorine because fluorine is really good at attracting electrons. So the electrons are going to be gathered around the edge here, which makes the inside part, the nitrogen, a little bit positive. And so if you think about NF3, if I had another NF3 over here, this one hopefully kind of makes sense. All right, yes, there are electrons, okay? So it's not that there aren't London dispersion forces. There are, right? There are electrons floating all around here, and in a given moment, maybe all those electrons gather in one spot. So this would be a little bit negative. The other side would be a little bit positive. There would be some attraction. But the bigger player is the fact that this nitrogen is basically positive, right? This fluorine is way negative because it's good at attracting electrons. So if I look at this molecule and I look at this molecule, the positive nitrogen is going to be pretty nicely attracted. That's why I'm drawing it with a dashed line, right? It's not a bond, it is an attraction, right? The nitrogen is going to be pretty strongly, mildly, moderately attracted to the fluorine, okay? And this is what we call a dipole-dipole force. I abbreviate it as dip-dip, just because that's a lot more fun to say. So we got LDFs, we got dip-dips. Dip-dip, dipole-dipole forces are going to be at play when you have a polar molecule. So if you go through the rigmarole of drawing the Lewis dot structure, of thinking about the electronegativities and determining, once you've used SNAP, if it is asymmetrical and it's a polar molecule, if you've got a polar molecule, you know that you're going to have not only LDFs, because everything has electrons, but the more important thing, what's going to create all the properties of these particular molecules? These ones, these are moderately strong, because we know that positives and negatives attract each other. It's just the way the universe works. So these are going to typically be stronger than your London dispersion forces, which means that if I had to compare like a CH4 and NF3, I'd look at the CH4 and say, oh, dude, that's wimpy. That is non-polar. It only has LDFs. This one, NF3, is going to have LDFs because, yeah, it has electrons. But more importantly, it's going to have dipole-dipole forces. And because dipole-dipole forces are stronger than LDFs, if I had to say which one of these is going to hold on to its neighbors more strongly, NF3 holds on to its neighbors more strongly because dipole-dipole forces are the stronger of these two. So that means that if NF3 holds on to its neighbors more tightly, it's going to be harder to separate from their neighbors, which means that NF3 is going to have the higher melting point, boiling point. CH4 is going to have the lower melting point, boiling point. All right, I'm going to pause, go back out to look at you guys, because this is the hardest part of doing this over the computer. I can't see your faces. I can tell in the classroom by looking at you all in a heartbeat that you don't know what the heck is going on. Here I'm having to look at these tiny little windows and try and figure out what the heck's going on in your heads. Ask questions if you have them right now, guys, because this is tough stuff. If this is your first class, this was a tough one to jump in on. All right, the good news is we only got one more and then we're gonna call it a day, okay?
I
All
have
right.
a question.
All right, Swasti, go ahead.
So is it possible for like the all of them be like negative and it still be polar?
All of them to be negative and still be
Like,
polar. I'm not sure I'm following you. Can you give me a little bit more there?
so you know, you have like NF3, right?
Yes.
And what if we had like carb CF3 or something?
Okay.
What if the middle one was negative?
Okay, so short answer is that won't happen.
Oh,
One
okay.
of them would have to be positive, the other one would have to be negative. Yeah, so you would never worry about that. Okay, Swasti?
Okay.
Okay, good question though. Anyone else?
Mr. Caldwell,
Is that Grace? Yeah, go ahead.
if the LDFs are only for nonpolar molecules, how are they also in the polar molecules?
Okay, that's a good question, and I was trying to get that in there, but it's really hard. LDFs are going to be present in anything that has electrons, and so it's going to be present for every single thing that we look at, present in anything that has electrons. Because the whole reason that LDFs occur is because of that temporary arrangement of electrons. If I think about just a carbon atom, carbon, it's got a mass of 12 there. So think about the electrons. If all the electrons in that carbon atom, and I'm not drawing the right number of electrons because I'm just not, but if all those electrons ended up in one spot at one given time, this part of the atom would be negative. The other part would be positive. So Grace, the answer to your question, even though LDFs are present in every single thing, because NF3 has a polarity, it has a dipole-dipole, right? Dipole means that it's got poles. The dipole-dipole is what explains why this guy has such a higher melting point and boiling point. It's not that it doesn't have LDFs, it's just that that is not very important when we compare it to the strength of these forces. This guy, the only game in town, the only forces that are interacting here are LDFs. So you kind of do a comparison. This one only has LDFs. This one has LDFs and dipole-dipole, right? Since dipole-dipole is stronger, this is why it has higher melting points and boiling points. Did I get to your question somewhat?
Yeah, I just don't understand why, like, it says that it's only in nonpolar if it's in both of them.
Is that because of what it says on the note sheet?
Yes.
Where is it saying that? I'm just trying to find it.
Found in molecules that are nonpolar. Right at the top.
Hold on.
You circled it?
I circled it.
Nonpolar.
God, I'm sorry. Hang on.
Like where it says
It's over here in notes, right?
No.
No.
The middle column that says
Okay.
found in molecules that are nonpolar.
These are the joys of doing this online. Okay, so the molecule, if it is nonpolar, it is only going to have LDFs, done and done.
Okay.
If it is polar, all right, it is going to have LDFs and dipole-dipole, but we don't really care too much about the LDFs because the dipole-dipole is much, much stronger, all right? Does that
Okay.
make a little better sense?
Yeah.
Okay, all right, again, I apologize, thank you for your patience. All right, last one, guys. You guys have been troopers. All right, we're going here. And the nice thing about the last one is it's just a special flavor of dipole-dipole. So it's called hydrogen bonding, H bond. All right. And the hydrogen bond is special, right? Hydrogen, if you go back and think about it, it's one proton and one electron. And if we think about hydrogen attached to these three elements, fluorine, oxygen, nitrogen. Fluorine, oxygen, nitrogen are the most electronegative elements in the periodic table. Because they are extraordinarily electronegative, they are extraordinarily good at attracting electrons towards them. Which means that this hydrogen, which just doesn't even stand a chance, all right? If H is bound up with F, if H is attached to O, if H is attached to N, in essence, this H is a bare naked proton. Oh my God, I said naked. And this guy over here is a wicked negative charged. And so if I think about another HF molecule over here, here's H and here's F, wicked big negative charge, bare naked proton. Do you think this bare naked proton is going to have an attraction for this very negative fluorine? You're darn tootin'. So the H bonds are the strongest of the three of these that we're talking about. Strongest intermolecular force. So, careful. A hydrogen bond only occurs when H is attached to one of these three things. These are three examples of where hydrogen bonding occurs. And you'll notice H2O. H2O is such a special molecule. It literally is allowing the chemistry of life to happen. And it has, relatively speaking, a pretty high melting point and boiling point. It melts at 0 degrees Celsius, 32 degrees Fahrenheit. That's way warm, okay? And the reason it has such a high melting point, high boiling point is because of the hydrogen bond. There is a great attraction between the negative oxygen and the positive hydrogen. Huge attraction between the positive hydrogen and negative oxygen. So hydrogen bonds, if we see hydrogen bonds, we're gonna be like, oh dude, they're wicked strong. So they're gonna have really high melting points, really high boiling points. The example that's provided here in the notes, water boils at 100 degrees Celsius. CH4, if we go back, remember CH4 was a non-polar molecule. So what's the only intermolecular force it played? It's gonna only have LDFs because it's non-polar. So this guy holds on to its neighbors really weakly, really sad, pitiful even, okay? So these are the three. And if I had to summarize them all right here, I'm gonna go ahead and make this go right here. So the weakest is LDF. Everyone has them. And for non-polar molecules, that's all they have. There's no other thing that they have intermolecular forces. Dipole-dipole are sort of the middle of the road, all right? And the only ones that have them are going to be polar molecules. Now, if you take it one step further, if you want to talk about hydrogen bonding, H bond, these are going to be the strongest of our IMFs, intermolecular forces. The hydrogen bond is just a special flavor of dipole-dipole. It just happens to be a polar molecule that has H attached to F, O, or N. And the way I like to teach students is, hydrogen bonds are fun. They're fun. They're fun. You say it weirdly, okay? Or if you don't want to say it that way, you could say that there's, hydrogen bonds are enough. Enough. I don't care. I'm literally just trying to make some sort of amusing thing out of this that is really not that amusing. So I apologize. Not really. All right. Oh, Lord help us. I'm going to stop sharing here because that was a lot of stuff. I'm going to also, where'd we go? Okay, there we are. I'm going to stop the recording.